Hello and welcome back. Today's topic is getting real-world analog information in and out of our microcontroller digital world, involving analog to digital converters to get an analog voltage into the digital world, and digital to analog converters getting digital numbers, binary numbers, out to the analog world. Couple things, oops, too much, there we go. Ideally, we'll talk about digital to analog first, because certain types of analog to digital converters use the D to A in the heart of them. So even though analog to digital is more common, we'll talk about D to A first, if that makes sense. So in an ideal digital to analog conversion, I will take my binary number, or code if you want to call it that, and whatever that binary number is, it will correspond to a output that is some fraction of my full scale voltage, okay? So I get an output in steps of the least significant bit, and actually what the real output would look is more like this, right, as we go up and up and up and up. So as I set each bit, I raise the voltage the same amount, and I have this slope equal to one least significant bit, or actually one fraction of the output per each bit. And all these, ideally these step sizes are all the same. So anyhow, nothing's perfect. In the real world, the kinds of errors we can get offsets where it just misses the zero. The slope of this can be wrong. That's, often if there's a error in our reference voltage inside. Nonlinearity is pretty common, where some steps are big, some steps are small, big, right, small, due to the tolerances of the individual components inside the D to A. And if it gets too bad, we can actually get monotonicity. That's a mouthful. Basically what we're saying here is that as I increase bits, I can actually get a reduction in the output voltage in certain cases here and here, there and there, where the output actually goes down a little bit. That's less common than some of the than this problem here. But it's, look at the data sheet and be aware of what the potential is for this sort of thing, so you know when you if what you're doing is going to give you the results you need. How does it work? Well, basically, we have a digital value stored in some register which latches that value or holds it. We write to this register and it stays there. And we send that register, that value, to our digital to analog converter, which gives us the analog output. And the basic concept is we need an output voltage equal to the least significant bit 0 times 2 to the 0, which is 1, and then plus bit 1 times 2 to the first, bit n minus 2 times 2 to the n minus 2, etc., all the way up to n minus 1. And so if we have let's just say it's an 8-bit converter. So this is, the bit 0, and this is bit 7, and then that whole thing is multiplied by the reference voltage we supply to the D to A converter divided by 2 to the n, which is the total number of steps, okay? So we get an output between 0 and Vref in steps equal to size, basically 1 over 2 to the n. And, come on, there it is. One way to do this is a weighted resistor digital to analog converter. Now here I have Vref supplied there, and I have my binary number, which will switch each of these switches one bit. The most significant bit switches this switch, the least significant bit switches this switch. And remember, that's all computers are really, is a bunch of switches wired together. That's how they work. So this is our register that we're outputting, and the state of every bit in that register will determine whether that switch is closed for a 1 or open for a 0. And each of those register outputs goes to a resistor. This one has a value of R. This one has a value of 2R, 4R, all the way to the 2 to the n minus 1 times R, which go into the input of our op amp here, and it has a feedback resistor equal to R over 2, and it gives us an output that matches that equation. And this is an example of how, it's talking about op amps, how you use an op amp as a summing circuit. So we're taking each one of these bits, multiplying it by a resistor, so that's this term here, the 2 to the n minus 2, or 2 to the n, or 2 to the whatever, multiplying it by the resistor that correlates to that amount, and then the feedback resistor here. And we have essentially a circuit that adds and multiplies all at the same time and gives us the V out according to the equation here. The advantage of a scaled or weighted resistor digital analog converter is it's fast, right? Is I just need to latch that register, and the only time limit is how long it takes this op amp circuit to settle, which is typically fairly fast. You can see a couple problems here as we get to large numbers of bits. I need a lot of resistors, first of all. That's not the big problem, but the range of sizes from R to 2 to the n minus 1 times R, that can be easily a factor of 1,000 in terms of the relative sizes. And when you've got a resistor that's, 1/1000th of another resistor, and if you expect to make it significant, make it count in the circuit, they have to be very high precision resistors. So that's the issue there, but it is, if you need speed, then you pay. A similar but less demanding implementation is the ladder digital to analog converter. The advantage here is there's only 2 resistance values, so it's not quite as fussy about that. And you have a voltage divider, resistor divider network. One end of this network is connected to ground or 0 volts, and then here, this is your register with the digital to analog or digital binary value that's going to be converted to an analog signal. And as you switch those switches, these resistors are connected either to ground like this, or they're connected to VREF like that. And the sum of all those voltages and things from that divider gives you an analog voltage here, which correlates to the analog voltage you want to output. And here the op amp really just serves as a voltage follower to so that you're not loading the circuit here. You want high input impedance so you don't affect the resistor divider, and it gives you a low output impedance to make it easy to send the signal somewhere wherever it needs to go. And you get basically the same equation that we had before. Okay, it's not quite exactly that. You get you get, instead of getting VREF totally, if you have all the bits set, you get you only get 7/8 of VREF. But that's you can account for that. That's not a big deal. Just need to be aware of it. And since you're not actually designing these chips, you're buying them. That's not a big deal. And the other thing, depending on the actual chip you're using, if we were to substitute a V minus instead of 0 volts for here and here, we could get an output that had a plus and minus, or bipolar output, where 0 would be 0 volts, and you could have a plus and a minus relative to that, if desired. Now, the problem with those, of course, is those resistor devices, we rely on voltage dividers and things, and they take a lot of precision resistors. The notes here say wasted energy dissipated as heat. That's not a big problem just for a digital to analog converter, but when we're using analog controls for to control a load, let's say we're controlling a motor, if I have, I'm going to draw, let's say, plus 12 volts here, and I've got my my analog device here. I'll draw it as a transistor. Just for the sake of drawing. And that goes to my motor. And that goes to ground. Okay. If I want to control this motor, I've got 12 volts here. I want to control the motor at equivalent to 6 volts here. And let's say it takes 2 amps to run that motor. Since I have 12 volts here and I want 6 volts here, it means I have to have a voltage drop of 6 volts across that transistor. 6 volts times that 2 amps, because they're in series, gives us a total of 12 watts of power being dissipated across that transistor or transistor-like device. And I have 12 watts across my motor as well. But this 12 watts I have across this controlling device, this analog control, it's wasted energy, and it's also just a ton of heat, right? To have that thing dissipating 12 watts, you need a pretty hefty-duty transistor to do that. You know, heat sinks, all kinds of things. Now let's suppose instead of trying to control that as an analog thing, I controlled it simply as on-off. And I'll draw it as a switch, just to emphasize the on-off nature. So I can have it off part of the time, and I can have it on part of the time, and then I'll turn it off, and then I'll turn it on, and then I'll turn it off, okay? And instead of seeing 6 volts here, I will see either 0 or 12, okay? And instead of 2 amps, I'll see 0 or it'll be something larger than 2 because I don't have that series resistance. You know, we'll say, just for the moment, we'll say 4. But on average, you know, if I were to do a time average, I can control that on-off rate up here such that I get an average equal to the 6 volts and 2 amp that I wanted to begin with, okay? Kind of hard to read when I write on top of a drawing, but I don't have much room to draw. So when I do this, if this is a solid-state switching device, when it's on, I may get a voltage drop across, say, of 0.2 volts, and 0.2 volts, and the current is 4 amps instead of 2 times 4 amps equals 0.8 watts to dissipate across that device. It's still some heat dissipation, but it's a lot less than the 12 that we needed the other way. So you can see where using a switching control can be a lot more efficient because we don't have that wasted energy dissipated as heat, and it also makes it easier to implement because I don't have to have a device that has the kind of power dissipation capacity that I would otherwise need. So that kind of leads us into PWM as a general thing, and here we're in specific, we're talking about PWM as a way to get an analog output. But a PWM it's a rectangular pulse wave, on and off. The duty cycle controls the average voltage, okay? We typically turn that on and off at a fairly high frequency. You will pick a frequency high enough that depending on the kind of load we're sending it to, it appears to be just an average. If necessary, we can put low-pass filters to remove the sharp transitions, and we'll look at that on the next slide, I think. But the efficiency is real good compared to trying to control things analogly, with an analog method. And over here on the right, you can see 0% duty cycle, it's off all the time, 25% duty cycle, it's on 25. And this command right here is an Arduino command, where 255 is 100% duty cycle. That's basically 8 bits. You know, so it's a 1, 1, 1, 1, 1, 1, 1, 1 as a binary number. And And, that's what the waveforms look like. And you could do something with analog circuitry as well, but that's not so common. But that's how you create, that's, what a pulse width modulated signal is. And we can use that PWM in our circuitry here as essentially a poor man's digital to analog converter, because the output is, the average output is a function of how long it's on versus how long it's off. So here I have one duty cycle. Here I can change the duty cycle and make it much larger, and my average voltage is higher. There's a time period here for each pulse. That's the base time in the duty cycle is the percent of the time on. Okay, and if I want to use it as an actual analog voltage, I would have my pulse width modulated output here, an RC network there where this PWM is going to charge the capacitor when it's on, and it'll slowly discharge when it's off. And we could calculate the time constant for that RC circuit to get the appropriate smoothing. I run that into an op amp here to give me the voltage out. This is just a voltage follower. It gives me the voltage out that I need without, loading this RC circuit here and draining the capacitor. And so that works good to get an analog voltage. If I'm controlling a motor or a light or something like that, I don't really need this stuff. Just the mass of the motor and inertia and the time constants of the mechanical system will act as a low-pass filter for me. So if I'm controlling a motor, I can just send that pulse width directly to our motor controller. It's unipolar. It only goes between 0 and the reference voltage. You can't get negative voltage. It's best suited if you need an analog voltage, but you don't need a high-resolution digital analog converter. And pulse width modulation in general is most commonly used with controlling motors and that sort of thing, where you want to control a lot of power without the inefficiencies associated with analog amplifiers. Let me get caught up here on my paperwork. So that's the same thing. Okay. Now let's go talk about getting information into our computer. We live in an analog world for the most part. We need to take our analog signals, our analog voltages, and somehow get them into the digital world so I can store them as a binary digital number so I can do math inside a binary digital computer. Again, analog to digital converters are not ideal. Ideally, we would get this behavior over here where the input voltage rises, and each time we cross the appropriate threshold, we switch yet another bit. Okay. Obviously, anything in between these threshold values we can't see, so we only, our resolution is limited here. So we do lose information every time you do an analog to digital conversion, because any voltage going on in between is just lost. But then there's errors, same kind of errors. You can get the offsets, you can get the gain error where the slopes are wrong, you can get nonlinearity where some of the steps are big, some of the steps are small, and potentially if it gets nonlinear enough, you could actually miss some steps where it should have stepped here and it didn't, and that's less common. But how does an analog to digital converter work? One type is the flash analog to digital converter. Basically, you just set up a whole bunch of comparators. If I have my voltage in, and I say that I have a comparator here, an op amp essentially, where the input here is, say, 1.25, and that goes in there. If it's greater than 1.25, that's on. Then I compare it to 2.5, and I compare it to this voltage, I compare it to that voltage. And I just have all these comparators. And it's fast. It's essentially instantaneous. But, you know, it's expensive, right? You know, if you want 8 bits, that's 254 potential output values, so you need 254 comparators. You can see how that would add up if you want to do 10 or 12 bits, which is even probably more common in terms of A to D precision. So you can use a truth table to get the output values, where you just look at the voltage comparator values and set the appropriate bits. A flash A to C, yeah. So there's a picture of it there. Okay, so you have your voltage reference, and it runs through this voltage divider network. So I get a different voltage at each one of these points. This is my input voltage. My input voltage, it goes to these op amps as comparators, and then there's the logic in here, which gives me a digital number out at the end. Okay? Some of the problems, if the input is changing during the conversion, you get erroneous values. You need to provide a sample and hold on the input. Sample and hold is just, we talked about that. So we use the sample and hold to hold the voltage constant to avoid this problem. So basically, the sample and hold, if I have V in, I send it through a switch, electronic switch, obviously, charges a capacitor. So when this switch is closed, that's the sample. It'll charge this capacitor up to whatever my input voltage is. Then I open the switch, and now this capacitor will hold the value of V in, and what we typically do is it will go into an op amp as a voltage follower, because the op amp has a very high input impedance, so we don't drain that capacitor, and then this goes into my A to D converter. So I close this switch before I convert, open the switch, and then I can do the conversion while that switch is open, and this voltage will stay very close to being equal to constant value. So that's typical for almost any A to D converters. You really want to use this sample and hold. Solves a lot of problems for you. Many converters have that built in, you know, like the Arduino or the Atmel chips that Arduino uses have that built right into it, so it just happens for you. You know, the output is valid only a specific time after the input is held. Well, eventually this will decay, but what typically is done is when the conversion is done, it will latch the values into a register here and store them there. So you have that value available to you until you read it. You can use this gray code thing. It's not common. Requires just a ton of comparators, right? And you know, each comparator has to have a monotonic range change. That's not, you know, it's just saying that the voltages have to continue to go up as you go up the ladder. But anyhow, move on. Successive approximation is probably the most common A to D converter. It's slower for a couple of reasons. One, it involves you're doing comparison, and the comparison is done compared to the output from a D to A converter. So the time it takes for the D to A converter to get a value latched in and stabilize and output the right voltage, that's a delay. And then you can do the comparison, and that takes time, and et cetera, et cetera. So it takes more time than the flash. Most applications it's fast enough, but it's less expensive to send to a higher precision. You know, 10, 12 bits are pretty common nowadays. the actual precision in terms of how linear and stuff is limited by the quality, right? But the idea is you start checking bits in the highest order bit. So you set your digital to analog converter all to 1, and so that's your reference. And and you just go through this loop comparing the bits to the input voltage, is the D to A, and if it's higher or lower, you set or clear the next bit down and go along. And it's kind of it's essentially you're comparing, if this is my voltage range, I'm checking for the voltage above or below this, okay, by setting just the most significant bit. And if it's lower, I'll set this bit and compare. And if say it's higher this time, so I set that bit and that bit and that bit, and I can hone in on it, by checking it in halves, the binary search. Here's a drawing of how it works. This is my analog input. This is my digital to analog converter, which has the reference voltage. So we latch a value into this. It sends out a voltage. We do a comparison. We check the comparison, say, is it higher or is it lower? And as a result of that, we'll change the value we output on that 8-bit, this digital to analog converter. And as we do that binary search, eventually we run out of bits, and then we send the output out this way. And we have start of converter, end of conversion, and an oscillator to control everything. They're fairly expensive because there's just a lot of monkey motion in there. You've got comparators, you've got the digital to analog converter, you've got the latching and all this. On the Atmel chips, like in an Arduino, a lot of them will have 8 analog inputs fed to a single converter with a multiplexer. And a multiplexer is just basically a switch which will select one or the other, either at command or one after the other successively in time. And so that when you do multiplexing like that, the time it takes to do all of the A to Ds depends on the number of channels. If I'm just using one channel and A to D over and over and over and over, that takes some period of time. But if I'm doing 8, by the time I go through all 8 of them, it takes 8 times as long. Duh. And again, we use the sample and hold before we get there. Integrating converters are the slowest, but they are the cheapest, whatever, you pay for speed. They can be pretty precise if you use good components, and they're used in DVMs and things like that, where the update rate is not very fast, and we use the time to charge and discharge a capacitor to figure out the voltage. How do we do that? Okay, let's walk you through this. I have a capacitor here, and it's connected to my VCC. And when I'm not using it, this capacitor is connected to ground through this transistor here, okay? So that transistor connects it to ground. My voltage on that capacitor is going to be 0. At some point, I decide to start my conversion here, and in this flip-flop, I will set this equal to low, and this goes high. The output in Q and Q naught from that flip-flop. When this output here goes low, that turns this off, and this capacitor will start to charge, right? This capacitor starts to charge up like this. And when the capacitor matches the input voltage, which is right there, and it compares in this op-amp, essentially, as soon as this capacitor voltage gets above the input voltage, my output here goes high. And when that output here goes high, it resets this flip-flop. This goes high. This comes low. Okay? So my signal out of the flip-flop is a pulse of some duration. if I took that pulse, and this is happening all the while we're doing everything else, and I have this oscillator here, which is just giving me an on-off, and I do a not an and, so that with these two signals, and what I do is, what I end up with out here is a, instead of just one pulse like this, or a number of pulses like that, I end up with some number of pulses that correspond to the oscillator frequency and the duration of this pulse, which goes back to the amount of time it took to charge that capacitor, okay? So if I count the number of pulses during each of these conversion things, given the number of pulses, that tells me the time, and knowing the characteristics of the capacitor and the current that I've been supplying, I can convert that to a digital number and send that to our computer. And those are the basic things, basic technologies. There's nothing magic. You know, things to be careful of. You know, you want sample and hold. Anytime you do analog to digital, you want to do anti-aliasing. And we talked about that in class. For those not taking this class, I guess I could do a video. Or you just look it up. Aliasing is a really, really, really bad thing, okay? You do not want that. And like I said in class, if there's one thing and one thing only that you take away from class, that's the bad things that happen when you get aliasing, okay? I'm going to babble about that for a minute. If you already know that, hang up now. You know, basically, if I have a noise frequency here, and if I sample it quickly, I get a pretty good representation. But if I sample it infrequently, say I sample it here, and I sample it here, and I sample it here, and I have to go backwards a bit, you know, what I will end up with is a low frequency signal in my digital world that didn't exist, right? There was no low frequency signal looking like this in this high frequency scribble that I drew, okay? So we create a signal out of binary magic that didn't exist. And an example would be, let's suppose, you know, you're an engineer working on tuning a suspension in a car on a test track. You're driving the car, and the test track's got some sine wave surface. That's not uncommon. They have sine waves of different wavelengths on the cast into the test tracks, and you drive across those different speeds so you can excite the car at different frequencies. And you may be exciting the car, and something is resonating and bouncing at this high frequency, but because you're testing for hours, you picked a really slow sample frequency to store your data because you don't want to have to deal with terabytes of data. And when you get back to the office to analyze it, and you do wait till you get back to the office because otherwise you're going to get car sick trying to analyze data on a laptop in a car that's going over sine waves. Trust me on that one, okay? You're going to, instead of seeing this high frequency signal, what you're going to see, and if I'm clever with my erasing, I can actually do this, you're going to see this low frequency signal, and you're going to say, oh, well, the car is floating up and down, there's something happening, you know, and you try and tune your suspension to get rid of this signal here, which didn't exist, right? And it's just not going to work. And it's been done, and people make this mistake. So you really want to understand the pitfalls of this conversion from analog to digital world. So, okay, at that point, I'm going to get off my soapbox, say thank you for listening, catch you next time, later.